Good morning. I think we can start. Today, we'll be studying PRI types, and then we'll focus on stagger PRF processing, and then filtering, Doppler filtering, which is a very critical concept in speed measurements. Finally, we'll be doing FMCW radar that you have been studying in the laboratory. As far as I remember, you studied for components, for models. So next week's probably you'll be building your own radar. Okay, let's remember the first lesson again. We got a pulse sequence here, as you see, and echo signals right here. Here is the parameters that we have been studying. Pulse repetition interval, pulse width, peak power, average power, duty cycle, and we assume that the PRI is somehow constant in all our previous analysis. Now we'll be looking at how we vary this PRI, what types of PRIs are commonly used in radar systems. Okay, I have here you see a slide where we have a list of PRI types. By the way, I will use PRI and PRF interchangeably. Sometimes I may say PRF, sometimes PRI. Remember that one is inversely proportional to the other. So it doesn't matter you use either PRI or PRF. Okay, the PRI that we have been using was actually stable type, where we got a constant value, constant PRI, and it does not change with the operation, with the scanning. Next, we got staggers, dual and switch, linear sliding, sinusoidal, and jitter. There may also be some pulse group repetition intervals where we get a group of pulses transmitted in a PRI type and another group of pulses in another type of PRI. So we may talk about somehow group of pulse, modulation of group of pulses. Okay, here you see a stable PRI where we got number of pulses right here, and here the PRI value. As you see, it's almost constant, 10 milliseconds. So if we try to, again, illustrate the radar waveform with infinitely thin pulses. So we got pulses like this, and this distance, yeah, all are approximately 10 milliseconds. Okay, we say approximately because in practice it's not easy to achieve to tune the system at exactly 10 milliseconds. There's always a jitter, a time shift or time drift, which cannot be controlled. So we have a little bit variation there, but it's quite small. It's called unintentional variation, jitter. Mostly it's less than 1%. Staggered PRI, we got we got several PRI values and we switch between them. Here you can see we transmit the first pulse with PRI 7 milliseconds, and then the next 10 milliseconds, and then 12.5 milliseconds. And then we drop 8.5 milliseconds, and then again 7 milliseconds. So we got one cycle here, simply, and then repeat it. Okay? We'll be discussing this PRI type extensively in the next slides. It's very critical. The goal of this type of PRI is to remove or eliminate blind speeds in MTI system. We have already given 2 stagger system in previous lesson. The one and switch, here we transmit a burst of pulses with a PRI value, and then another burst of pulses is transmit another PRI, and then another PRI, and then another PRI here. So it's just like stagger, but instead of transmitting single pulse at any specific PRI, we transmit a group of pulses, burst of pulses. It's used for resolving velocity ambiguities in pulse Doppler radar. Linear sliding, it could be up sliding or down sliding, depending on the slope, depending on the variation of the PRI. If it starts from a value right here and goes up to 10 milliseconds here, for example, with a positive slope, or it might start from 11 milliseconds and goes down until 10 milliseconds, for example. So this is used for constant altitude coverage for elevation scanning. And usually the max and min of this PRI values are determined according to the distance, the coverage that we would like to get. Sinusoidal or wobulated, it's mainly used in missile guidance, especially conical scan tracking. And we got, if we draw the pattern, as you can see, we simply have a sinusoidal variation. You see? So it repeats itself at every 10 pulses right here, approximately. The variation is here maybe up to 5%, depending on the requirements, of course. Jittered, this is intentional random variation. We tune the transmitting system to a random number, you may imagine, and we determine the PRI for each pulse or for each group of pulses, and it's not easy to extract the PRI values as it is generated by a random number. You see here, for example, if we make a plot, I'm sorry, this just like this. Okay, so random variation we see. It's not easy to extract the pattern, but there may still be some methods to do this. It's quite valuable for jamming, signal jamming. Okay, so this was a very short review of PRI systems, PRI types, sorry. And now let's look at the stagger PRF, which is very critical concept in radar systems. As we said earlier, it's used for resolving speed ambiguity, so reducing blind speeds. Here in this slide, we see two PRF system. So we got two PRF values. Here, the PRF values. And remember the delay line canceller. The response of delay line canceller was given, as you might remember, 2 sine pi FD FP, right? This was the response. So here FD is the Doppler shift, or it might be just F here, but I just write FD. And FP was the PRF. So if you look at the, if we plot this transfer function, we see this solid line here. So for every F2, let's say, value, we got a blind speed. So here is the first blind speed, here is the second blind speed, and then third blind speed. Now, if we change the PRF, then the response, so the transfer function will be changed, and we get this response here, where we got a blind speed at F1 here and 2F1 here. So if we change the PRF from FP1 to FP2 and continue FP1, FP2, FP1, FP2, then the delay line canceller will get a first blind speed at the frequency where both PRF give us blind speed, okay? In this case, for example, this is 2F1 or 3F2. Okay, this is how we increase the value of the first blind speed. We change PRF, and the blind speed which is the same for both PRF will be the blind speed that we'll get at the DLC, delay line canceller output. So then if I increase the number of PRF, then I simply increase the first blind speed. I can push the first blind speed to the right here. For example, if I take another PRF like this, okay, then the first blind speed will be pushed ahead, and then we'll not get any blind speed when I use more than one PRF. And the number of PRF will determine the first blind speed, actually. Higher the PRF values, higher the first blind speed. Okay, here how we simply formulate this. Let's take P stagger system. So I have P pulse repetition frequency. And I just look at the greatest common divisor, GCD, of this PRF. And I determine the stagger level, K stagger. And in this example, for example, for you can see on the slide, we have 750 hertz and 1000 hertz. So this is PRF1 and PRF2. And let's see the common greatest common divisor in here, 750 and 1000. It's going to be 250. Okay, so then we talk about 3-4 stagger system. And let's see how much we change the first blind speed when we use this system. Before that, of course, let's determine the first blind speed by taking the average of these two. If we have no stagger, so unstaggered case, we can determine the average PRI, which is calculated from the two PRF values, and it's 857 hertz. And then the first blind speed is going to be the values of integer multiples of this 857 hertz. Okay, so if we simply show it, here is the first blind speed, and then if this is FP average, then this is going to be 2 FP 1 average right here. These are the first, this is the first blind speed and the second blind speed for unstaggered case. If we use two staggered, then the greatest common divisor was 250, and then the staggers is going to be 3-4, and the first blind speed will be the least common multiple of these two PRF values, okay, which is 3000 hertz. 3000 hertz, which means that your first blind speed here from 857 goes up to 3000. Okay? You see? So if we push it 3.5 times ahead, this is a quite good method then, right? If we increase the number of PRF, we expect to increase this, of course. For example, if we take another combination of these two, we can add one more and then increase this 4 kilohertz, 5 kilohertz, or 8 kilohertz. Here we have a problem from the textbook. Actually, we have some hint here. Some of the students have already asked about this, and then I just give this number. It's an S-band radar, and the stagger levels or PRFs are given here. The first blind is asked, and this shows how much you change the first blind speed, push first blind speed from a value that we have, just like we have calculated, we have determined in previous slide. Okay, usually there should be somehow an algorithm that can generate these numbers. So if we tune the PRF values, then there should be a computer search algorithm that can determine the blind speed for any number of PRF values. Okay, it's not, that easy to find a number here. Okay, it's easy for 250 and 1000, but if we take here, for example, 1022, 1031, and 1138 and 1000 hertz, it's quite complicated. You have to do some searching, and there may be some algorithms or simple search methods that you can develop. Okay, so how do we process staggered PRF signals? You might remember this slide from previous lesson. This was a delay line canceller system. Somehow it's called transversal filter. We got an input signal here, x of t. It's not delayed, it's weighted by omega 1. And then it's delayed by t1, and then weighted by omega 2. And then delayed again, t2, and then omega 3. So we have here a summation of exponentials, actually. We have already derived this previously, as you might remember. We got Dirac delta at the input, and then shift this Dirac delta by t, and they get the difference. For constant amplitude, unity amplitude, we take its Fourier transform, and we get that an exponential appear in Fourier transformation, which means that your transfer function is given in terms of exponential. So here we got the summation of those h of f, actually, and then we got the summation of exponentials with different phase and with different weights. Okay. So how do we select the number of delay lines here? So simply taps. How many taps are we going to use? And how do we choose weights? It's about how to design filter. And as you may know, this is not a filter design course. This is an introductory course to radar systems. So we are not going to give full details, full design of filters in here, but we just want to give some basic principles of how we implement filters in radar systems. Okay, here is a filter response. So just like this transfer function, you imagine, more realistic one. This is 4 periods, so 5 staggers. By the way, here, stagger number and periods are different. We have to be careful here. Let's show it. Okay. Okay, let's say this is T1, T2, T3, and T4. So we have 4 periods in here, but we have how many pulses? 1, 2, 3, 4, and 5. So 5 stagger, 4 periods, okay? You have to be careful here. This is an MTI air traffic control radar filter response. There are 1, 2, 3, and 4 periods, and amplitude weighting of dual canceller. So 2 DLC, where this means that I use 2 delay lines. Okay, so that the transfer function was already given in previous lesson. I'm not going to repeat that. This is just the result of the that system. I mean, we do not give any more details or derivation of that, but we can try this. Here is how fixed PRF and staggered PRF are different from each other. As you can see, we got here responses where we got blind speeds. Now, at this blind speeds, the staggered PRF is not 0, as you see, right? We are still able to measure the speed of the target at this velocities. Okay, here there are 4 pulse periods. They simply take an average pulse interval and then reduce it by 5%, increase it 5%, and then 15% plus 50% minus, and create it for periods. And the weighting coefficients here are taken 7 divided by 8 and 1, as you see here, list of weighting coefficients. So the design of the filter, anyway, here is not seems to be very straightforward, but in practice there are too many things that we have to consider. So here we'd like to give only fundamental principles or concepts about filtering. Okay, another way, another filtering technique is to use Doppler filter banks, where we got contiguous filters that are placed over the band in which we expect Doppler shift side by side, and they are overlapping. And whenever there is a signal at a frequency that falls into a specific band of these filters, then we determine approximate value of the Doppler shift from the bandwidth of the filter. Okay, as you can see here, the response of the filter bank, we got, you see the first filter, let's say from 0 to 1. So whenever we got a Doppler shift falling into this area, okay, so this means that I get a response from filter 1. So the amplitude of the output amplitude of the filter 1 is relatively higher than the others. Okay, when there's a Doppler shift appears in this band. For the second, you can, for example, take here. So this region where there is a echo signal, there is a Doppler shift appears in this band, then I decide that that's the filter in which we got the speed. But it's not, of course, easy to estimate the exact value of the Doppler shift. So there is going to be an error here, but I may reduce this error by increasing the number of filters. So reducing the filter bandwidth. Okay, there are some challenges in here, of course. There may be some ambiguities. There may be problems in design of these filters because we talk about very narrow band filters, which is quite complex and costly. And there may be side lobes, for example, that we do not show in here. So there are too many challenges here, but the idea is simple. We simply divide the band into very small subbands. We design a filter in subband and then simply apply the output signal to all these filters and then choose the one that gives the maximum response as the Doppler shift. Okay, let's go back to transversal filters again and remember the filter response. Okay, let us again, let's go back to the single delay line case. If it is T1, we got an input. Okay, we add them up. Here is direct delta at the input. So the output is going to be direct delta plus minus direct delta t minus t. P minus T. Okay, so this is the impulse response of single delay line canceller. Now we can extend this by using n taps. So that's going to be a summation of difference of Dirac deltas. And if we take the Fourier transformation of this, we got the summation of exponentials in here. Okay, so this is just like extension of this formulation. Okay, we got n pulses and n minus 1 delay lines. Okay, we have to be careful here. And the time delay here will be proportional to the PRI, pulse repetition interval, because we collect echo signals if we consider a target at a range of R. We expect that we collect pulses from this target at every PRI, once every PRI. So that's why we use time delay as T here. And here, each here n taps, we got K outputs for each filter. And filter weights is going to be an exponential function, as you can see here. For n weights, we can define K filters. Okay, let's say 8 filters. And the filter weights will be simply extension of this exponential. We insert I and K n values and determine the weights. Okay, so depending on the number of delay lines, we can calculate the weights. In next slide, we have the response of this filter. This is a summation, as you can see here. Once we get its magnitude, we see that it's going to be sine pi nx divided by sine pi x. Okay, in this form. So if we plot this, we'll see a sinc type transfer function because it's just like a sinc function that we have studied previously, and its maximum will be at sine 0 to 0. There's the argument here should be 0 or multiple of pi's. And the main lobe width will be 2 divided by nt. So 1 over nt will be half of the main lobe. And then by duplicating this filter at different frequencies, we got filter banks actually, just like here. Okay, we have side lobes that we ignored here, by the way. Here is the side lobes. And the amplitude weights can be chosen according to the design requirements. And if we look at the processing here, we see that that's just like FFT, fast Fourier transform. And mostly filters are somehow filter processing is based on FFT in most of the current receivers. Okay, let's go into the details of MTI digital processing and show how to design a phase detector. Remember that the phase detector was the main component in MTI processing. We have to trace the phase variation in order to extract the frequency change, so the Doppler frequency. And the general receiver structure, a generic receiver structure for MTI is shown in here. The signal from the IF amplifier is split into two channels and applied to two phase detectors. Each phase detector is fed by a coherent oscillator, COHO, as we have already shown in the MTI block diagram last week. You may imagine that that's a cosine at a frequency, let's say, ft of t. So pi over phi shift produce a sine at the same frequency. Okay, so one phase detector use cosine, the other one uses sine, and then we got analog to digital converter, and then we got digital memory, digital processor, and then we got the magnitude and phase components, and then converted to analog if there is a display, an analog display for the operator. Okay, let's see phase detector. Remember the part of some portion of the MTI system. A phase detector is connected to a coherent oscillator, reference signal, and IF amplifier output. And the output of the phase detector is used in DLC that we have already studied in previous lessons. Now, here we have a phase detector block diagram. And it seems to be very complicated, but actually that's quite easy. The IF signal, amplified signal, which is typically a cosine with a transmit frequency and Doppler shift, FT. Remember that that's the received signal where we expect some Doppler shift. And there is going to be a constant phase shift. This is random, but constant. It does not change with time. And we applied this to a filter, actually two filters, two mixers, I'm sorry. You have already studied the mixers in the laboratory, right? We use a VCO, right? You remember? RF signal generator. And then we got IF or RF. This was the mixer that we used in the laboratory. So I'm sure that you remember this block diagram. So that's what we are doing here. So we mix a cosine reference signal with the received signal. Now the difference between them actually the Doppler frequency and fixed phase shift. Okay. Now this reference signal is shifted by pi over 2, and we got a sine. So cosine is applied here, and sine is applied here. So this is called in-phase component, the output of the mixer, to which we apply cosine is called in-phase component, while the output of the mixer to which we apply sine is quadrature component. So I and Q. So I refers to the component aligned with cosine. Q refers to the component aligned with sine. So 90 degrees phase shifted version. So what will happen? You simply multiply this cosine and this one, and you will get this difference. Okay? If we use a low pass filter, and mostly a mixer includes a low pass filter inside to remove harmonics. So we'll get a cosine at FT, the Doppler shift. I'm sorry, there should be a T here, by the way, it's missing. Minus phi, the fixed phase. Now, as we have I and Q, we can determine amplitude and phase of the signal. The amplitude of the signal is going to be typical complex representation. You remember, this is my I, this is my Q axis, and I just consider a vector here, okay, with an angle, let's say phi, and it rotates with a frequency of ft. So this is how we represent this signal, okay, a complex phasor. So it's going to be I plus JQ. Let's say X of t, I plus JQ. So I can determine its magnitude as simply I squared Q squared. The phase is going to be inverse tangent Q divided by I. Okay, you know this from EE 316 communication systems, where we studied INQs, or complex representation of modulated signals. So this is how we design a phase detector. In most of the receiving systems now, this is fully digital. So mostly they use FPGA or digital signal processors, where they simply convert the analog IF signal into digital and then create INQ digitally. Okay, and the computational capacity of that block is quite critical to detect the, or to achieve a high resolution phase or frequency measurements. Finally, here we got a comparison of MTI and pulse Doppler radar. We have already talked about MTI and pulse Doppler radar. We have given some fundamental operational principles of MTI and pulse Doppler radar. Here is a simple comparison of MTI and pulse Doppler radar. This is simply compiled from the textbook, not my view actually. In MTI, in the past, there was magnetron as a generator, while in pulse Doppler radar, klystron was used in, as far as in recent systems. I mean, today's technology may use different solid state generators. High power amplifier, analog DLC, analog digital filter bank. Now these are old. We have fully digital systems now. And these are the things that we have already given in the very beginning of the MTI and pulse Doppler radar concept. One has Doppler ambiguity, the other one is range ambiguity, and one is high PRF, the other one is low PRF, and it's quite related to the clutter level. Then in the pulse Doppler radar, as the PRF is high compared with the MTI, it receives more clutter. So clutter reduction is very critical in pulse Doppler radar. And here we see AVAX. It's a system, it's a platform which is used for surveillance and command control communication, 3C capability. We have currently, you know, Barış Kartal is quite popular and available in literature, as you know. There are 4 AVAX now in Turkey. South, as far as I remember the names, but west, east, south, and north. So 4 platforms, such platforms can simply detect any object moving in airspace of Turkey. So here we see the specifications that I compiled from open literature. There is nothing classified here. So it's better to stop here and have a break. Okay, about 10 minutes. Okay, let's continue. Now, in the next few slides, we'll be dealing with an air platform, just like AVAX, and try to see what happens in the spectrum, how much or how many different components will be seeing in the Doppler spectrum when there is a air platform flying over the Earth, and there is a target toward the nose of the platform. Okay, for this purpose, let's see what we transmit first. Remember, sorry? Sure. I'm sorry. Göktuğ admitted. Okay. Okay, let's remember radar waveform again. What we transmit, let's see first the waveform. We got a sinusoid, right? Gated. I'm not sure why this happened. Okay, sinusoid. On and off. So here is our tau, the pulse width, and here is the PRI. So let's say TP, which is 1 over FP. Okay. Now, if we get the Fourier transformation, Fourier transformation of this, okay, we see the spectrum right here. Okay, when we look at the envelope of the spectrum here, we see a sink-shaped why? Sink-shaped spectrum. This is discrete spectrum, which means that I have tones here. Okay, each is spaced by FP. So the distance between any two tones here is FP, and the first null of the sink function here is spaced by 1 over tau from the center. Okay, so let's say, for example, if my center frequency, the operational frequency of the radar is 1 megahertz, let's say. This is not realistic, but just imagine that that's 1 megahertz, and the PRF is 1 kilohertz, for example, or 10 kilohertz, let's say. And let's say tau is, let's determine TP first. It's going to be 0.1 millisecond, right? The TP. And tau, let's say, just 5 times of this, so 0.5 milliseconds. Okay? So what will happen then? On the spectrum, we'll get a peak at F0, so 1 megahertz. So let's say 1000 kilohertz. And this is the first peak. Let's show it in red. First ton. The next ton is just here. Goes like this. So the spacing here, right, is going to be FP, so 10 kilohertz. 10 kilohertz. Okay, and here it is 1000 plus, so 1 over tau, which means that 1 over tau is 2 kilohertz, right? 2 kilohertz. Sorry, it's not 2, I'm sorry. It's point, yeah, so there's, I'm sorry, there's an error here. I just put the numbers randomly here, but we have to be careful. Okay, if this 0.5, so it's going to be 0.05 milliseconds. I am sorry. So 0.05, 1 over 0.05, it's going to be 20, right? 20 kilohertz, yeah. Yeah, 20 kilohertz, so it's going to be 20,000 plus 20, which means that there is just one line actually here. Just one line. Yeah, and then 0. One line and then 0. Okay? As the TP is twice the pulse duration, so it transmits half of the time and then receives half of the time. So simply, the spectrum is, as you see, a discrete line spectrum, and we transmit many tones simultaneously, and we expect that the echo signal should involve each of these tones. Okay. Now, suppose that we consider only the main one here. Okay. We transmit a signal at F0. Okay. Imagine that we transmit single tone at F0, and what will happen at the receiver? Now, here is, let's say, AVAX. We have already talked about that. That's an air platform which has a radar, a long-range radar, and the antenna emits energy, and there is a main beam and some side beams here, side lobes in here. So consider the radar antenna, just like this. Again, very similar to sync shape. Here is the main lobe, and here is the side lobes. We directed main lobe into the area that we want to see. Let's say there's a target here. Okay, moving with the speed of, let's say, VR. And here is the direction of motion. And so there is going to be an angle here. And the side lobes emits energy in all directions. Okay. So we can expect echo signals from the ground. Here is the Earth. So we have scattering signals from the Earth in different directions. So there is going to be, for example, the energy scattering from this direction, from this direction, from this direction. When it is perpendicular here, it's going to be, the Doppler shift is going to be 0, as the angle is going to be 90 degrees, right? So then the echo returns from the altitude is going to be 0 at 90 degrees, okay? We have to be careful there. Then what will happen at the receiver? Okay, again, remember we transmit single tone here. We transmit only this one. We consider this one only, okay? Not the others, just take one. So what will happen? As the transmitter and receiver next to each other, then we expect some leakage from the transmitter to the receiver. So some of the energy from the transmitting antenna will be coupled with the receiving antenna, and then we can see a sinusoid at exactly the same frequency of the sinusoid transmitted by the same system, okay, by the antenna, by the radar, sorry. So what we expect, so here is the receiver pattern, sorry, spectrum. So we got a leakage first, a powerful leakage. Why? Because it's next to each other. The transmitter and receiver antennas are next to each other, and it should be a strong leakage at the center frequency. Next, we expect altitude returns. So some of the energy from the side lobes will be reflected from the ground. since we are moving in perpendicular, so 90 degrees, then we expect no Doppler shift. Okay, no Doppler shift at this altitude return. Then there's going to be an altitude return, let's say with a different color. Here is the altitude return. Oh, I'm sorry. Again. Here is the altitude return with no frequency shift. Why? Because the direction of the motion of the platform is in perpendicular to the direction of the altitude return. So the Doppler should become 0. A little bit spread, but it's a strong altitude return we expect. And there are side lobes, as we said earlier. Here we see some side lobes. So side lobes will be emitting energy into the space, into the Earth, and there may be echo signals from the Earth, but not 90 degrees. If we consider the Doppler frequency, so these are the components that are spread over frequency because of the motion, because of the angle, and we expect side lobe clutter. Let's make it yellow. So here is the side lobe clutter. So the width of this clutter will be proportional to the motion of the platform. Okay? Higher the speed of the platform, our system, so broader the width of the side lobe clutter. So here, as you see, the Doppler shift due to the side lobe clutter will be proportional to the speed of the platform itself. Okay. And there is going to be main beam clutter, which is, okay, now let's take this main beam. And here's the direction of motion again. So there is an angle here. This angle will determine the amount of the Doppler shift. This should be somewhere between the center frequency and the speed of the target. I mean, the maximum Doppler shift due to the speed of the target. Because this angle could be somewhere between 0 to 90 degrees. Okay? So here is the region of the angle. So it's going to be 0 to 90 degrees. So it should be somewhere here. So we can expect the main beam clutter right here. Okay? This is going to be simply 2V lambda times cosine this, let's say, theta main beam. Theta main beam. Okay? So here, this is the speed of the platform. Cosine theta m simply gives us the Doppler shift. So the radial frequency will be changed, and so the Doppler frequency will be changed for main beam clutter. Then we got receiver noise, of course, at background. Now we assume that that's quite low compared with the echo signals. Now, how about the target? If we got a target, let's say right here, okay, there is going to be a motion of this target, right? Or in that way, it's about the speed of the target, right? So let's say the speed of the target is Vt, then the Doppler shift is going to be 2 times Vt over lambda. Okay, so if it is coming to the AVAX system, then there's going to be a positive Doppler shift. So here is the Doppler shift of the target, and here is the echo due to the target. So in order to see the target, then we have to have a Doppler shift, which should be preferably out of the side lobe clutter, okay, so that we can detect it. If this is inside the side lobe clutter, then it may not be possible to detect that target because of the side lobe clutter. It might be the clutter or target echo might be less than the side lobe clutter echo, and then we cannot detect the target. Now we repeat this for every tone here. This is the first, the fundamental frequency. The next one, we repeat it again here, but for every FP. So every F0 plus NFP, we see the spectrum again and again. Okay, so this is how things are going on the spectral domain in a realistic system. And the objective of the system then is to detect this target echo, actually. And there are too many, you see, unexpected echo coming from different interactions. Okay, so this was about how to apply Doppler concept on an air platform and how to evaluate the spectral domain behavior of these signals. Okay, this is the last subject of today's lesson. It's about FMCW radar. And you have been working in the laboratory and you studied voltage controlled oscillators. Let us just try to remember that. Okay, in the laboratory, what are we doing? In laboratory, we got VCO, right? First, we studied VCO, and then we studied mixers, right? Mixer. What else? Filters and amplifiers, right? What else? Now, this week, you'll be studying antennas. Is that right? Antennas, yes. Okay, so we simply studied most of the main components in a radar system. Now, if we want to build up a radar, then we simply connect these components, these models, appropriately to transmit a signal and then receive echo signals coming from a target. Now, in this slide, we'll see a radar system that was built by our students in previous years. On the top, you see the main block diagram of FMCW radar. We got a signal generator here, which is typically VCO in our case. And we got a splitter where the VCO signal is split into two, one into the receiver. So this part is the receiver, by the way, and this part is the transmitter. And this, the output of the signal generator is split into two, one into the receiver, the other one into the antenna. There may be amplifiers in here, right? Power amplifier typically. Here we have a low noise amplifier, which is not shown in here. And two antennas we use. These are horn antennas. On the bottom right, you see horn antennas. One is for transmit, the other one is for receive. And we got mixer, which simply down convert the received signal by using the transmitted signal. And then we got the signal processing here and displaying, which is in our case is a spectrum analyzer. But we can build a digital system here. Okay, on at the top, at the bottom on the left, you see the hardware. We got VCO here and the splitter, and we got a mixer, and from the not all are shown here, but here is the low pass filter, and then here is the power amplifier and LNA, so 2 channels, and so then the output of this goes to spectrum analyzer. Okay, in the laboratory, after next week, you will build the transmitting section and then receiving section. Finally, you will build full radar system in the laboratory and do some tests with a metallic object. Typically, we use a metal plate of 1 meter squares or less in order to see the range or the beat frequency clearly and check the range of the radar in the laboratory. Since there are too many objects in the laboratory, we expect too many scatter echo from around, but still you will be able to see the target echo easily. And when you increase the range, you will see that the target echo will be getting difficult to see, but still up to about 20 meters or 15 meters, you can still see the target echo. Okay, you'll build that radar anyway. Now let's see how we analyze signals in this radar system. This is an FMCW radar, as we said earlier. FM is a modulation method, frequency modulation, as you know from the course EE316, frequency modulation. And for frequency modulation, we got a message signal. Okay, so we simply plot it, FM system. We got an input signal, let's say M of T, the message signal, and we got a carrier, C of T, let's say, and output is S of T, modulated signal. This is FM signal. So 2 signals are used in here. One is the message signal, the other one is the carrier. Okay, and we simply vary the frequency of the carrier in accordance with the message signal amplitude. If the message signal increases, we increase the frequency. If the message signal decreases, we decrease the frequency. So we then tune a frequency band. How much we increase the frequency and how much we reduce it. So there's going to be a bandwidth anyway. We tune it. Mathematically, that S of T here can be written with this form. From the communication systems course, you should know this. You might remember this easily if you look at that course material. Here we see we got the carrier frequency, so cosine 2 pi FCT, plus we got a constant, that's a tuning parameter, and integration of the message signal. Okay, so we integrate message signal. What will happen then if we get this part, a time varying phase, we actually tune the frequency, because variation of the phase, a variable phase, simply impose frequency variation. And here the center frequency or carrier frequency is going to be taken F0, which is the minimum frequency, plus B over 2. And the message signal here is taken as a triangle. Okay, triangle. Mathematically, a triangular signal is given in here. So just take a triangle. Whose duration is 2t, so let's say 0 to 2t0. Okay, whose amplitude is 1. So here is my triangle. Now, we got a sequence of these triangles, okay? So this triangle continues, okay? It's continuing from whenever you turn the system, it starts and then continues until infinity. So we talk about a sequence of triangles, so summation of triangles. So mathematically, then we can write a summation of triangles. Each is shifted by 2t0. It repeats itself at every 2t0. Is that clear? Now, use it into this equation and then get the FMCW signal. We can, for a single triangle, just taking one triangle only, the signal becomes like this. Okay? Here we got FC, the carrier frequency, plus a constant. We can tune this. A bandwidth, here is the bandwidth. Okay? And F0, again, here is F0. So we have this triangle here, and take one of this, and then look at the signal right here. So here is the FM signal. We're single triangle. So what we have here, we have a linearly varying frequency, okay? The frequency of the sinusoid increases in accordance with the message signal, triangle. When the message signal has the peak value, the cosinusoid has the highest frequency, which is F0 plus B. When it has minimum value here, the frequency becomes minimum, which is F0. Is that clear? Now, this is time domain FMCW signal. How about frequency domain? When we take its Fourier transformation, okay, of the signal in previous slide, not this one, by the way, this is the message signal. The previous FMCW signal has a spectrum of this, okay, or this. The center is F0 plus B over 2. The minimum frequency is F0 and maximum frequency is F0 plus B. So you can generate such a waveform by using voltage controlled oscillator, as you might remember. If we use a VCO and create a triangular signal, let's say this is arbitrary waveform generator, appropriately you tune it, and then use a VCO with some power supply here, you got the modulated signal, FM signal or FMCW signal, okay? And if you connect it into a spectrum analyzer, you will get this spectrum. This is very much like the theoretical one, right? It looks like theoretical one. The bandwidth here is can be measured from the minimum to the maximum frequency, and it's going to be B here. B. Now, this is a very critical parameter. You have to choose the bandwidth appropriately. It's about the resolution. I mean, remember the range resolution. It's about how well we detect or we discriminate two targets in distance, right? Let's say U2. If I look at you from that way, I will see two echo signals. But in order to discriminate these two echo signals, the range resolution should be half of that C tau over 2, right? So it's going to be C over 2B in here, so the bandwidth. So I have to choose the bandwidth here such that the distance between you should be measured, okay? So here is what we will see if there is a target, a fixed target, or a target is in motion, okay? The red one here, the red waveform, represents the transmitted signal, okay? And the green one represents the echo signal at a target, stationary target, which is, let's say, if the time difference is tau, then it's going to be simply the difference is going to be C tau over 2, okay? Sorry, it's about, I'm sorry, let's remember the distance. Let us write that. We got the transmitter here and the target here, radar. It's not clear. Okay, remember this. This here is the, let's say this is target. The distance is R. Then the time delay is going to be 2R divided by C. Okay? So if I have a stationary target at distance R, the time delay is going to be tau. So then an echo signal coming from this target is going to be the green one, shifted version. If there is a motion of the target, then if there is a motion of the target, if the target is moving, then we might see an echo signal just like the blue one, where the range is varying with the speed of the target. So the Doppler shift. Okay? Now, if we get the difference of this red curve, blue curve, and then yellow curve, we'll get bit frequency, which is used to measure the range and speed of the target. It's a very important parameter. I mean, the parameter that we would like to measure actually. Once we measure this parameter precisely, we can measure the speed and range of the target easily. Now, let us focus on this part of this curve. We see a time delay of tau in here, and the difference between the transmit and the receive signal in frequency domain is bit frequency, and take the maximum frequency here, or the difference between the minimum and maximum frequency as delta F, which is B here. So we can take two, we can consider two triangles. One is here, the other one is here. By using the similarity, I can write the bit frequency in terms of the parameters of the radar. These are FM, right? And DF, so delta F, sorry. The bandwidth and the pulse period, inverse of pulse period. So once I know these two parameters and the range, I can determine bit frequency. Or if I know the range, I can determine the bit frequency by using these two parameters. So here, two parameters are critical: FM and delta F. FM is simply the inverse of the modulating signal duration, and DF is the bandwidth of the transmitted signal. Okay, here we go. So there are actually two beat frequencies here, one for a stationary target, one for a moving target. And if you look at the bit frequency, there may be two different bit frequency for each of this. Why? Because since this is a triangular waveform, the bit frequency right here and right here are different. One is smaller than the other one. Okay? And usually we use both and get the average to estimate the bit frequency. Let's say one is uplink bit frequency. Okay? Uplink. So FBU, uplink bit frequency, and downlink or down bit frequency, not link, down bit frequency. One is the is due to the positive slope of the triangle. One is due to the negative slope of the triangle. So these have different values. They are not the same. The values are not the same. So we have to get the average of this to get the average bit frequency when we use a triangular waveform. When we use a sawtooth, for example, this is another modulating signal, just like this. Instead of a triangle, we can use sawtooth. Then we have one bit frequency. Usually, triangular waveform is preferred in order to measure the bit frequency precisely. Okay, so what will be the range? Then the range is going to be the average, you see, of these two. So there's going to be simply FBU, FBD divided by 2. So I just here rewrite this equation by replacing bit frequency by average of these two bit frequencies, up and down bit frequencies. Okay, and then determine the range. Similarly, using the range speed relationship, I can determine the speed. Okay, now from here, what we understand, once I measure the bit frequency precisely, I can measure the both range and speed. Okay, and the most important parameter here is the bandwidth, actually. Okay, because it gives us the resolution, and in very short range, resolution is very critical because there are too many objects around and you have to discriminate them, and it requires very good range resolution. Now, what specifications do we have in our radar system? The frequency range is, as you can see here, 4.4 to 4.9 gigahertz. So if we consider the triangular modulating signal, okay, then this should be 4.4 and this should be 4.9 gigahertz. Okay, this simply gives us the bandwidth, right, of the radar system. So the difference will be the bandwidth of the radar system. This is a C-band radar system, by the way, and by using the range resolution, this is not R, by the way, let's say delta R. It's going to be C over 2B, which is about 30 centimeters. So two targets spaced by 30 centimeters can be discriminated by this radar. So if you put two people, for example, and if the difference between them, if the spacing between them is only 30 centimeters, then you will see two peaks there. I mean, the bit frequency will be simply showing two targets there. If it is less than 30 centimeters, you will see a single bit. That's theoretically what you could see when there are two persons in the laboratory. The sweep time is triangular, so we use triangular waveform, and sweep time is sweep type is triangular, and sweep time is 100 microseconds, so 0.1 millisecond. Okay, so this duration, yeah, is 100 microsecond. So in every 100 microsecond, The sinusoid starts from 4.4 gigahertz and then sweep the band until 4.9 gigahertz, so 500 megahertz. The target range could be about 9 meters. In the laboratory we test. You can still measure more actually, but due to the scattering, you may not see a low RCS object, just like chair, for example. If you place a chair about 10 meters, you may hardly see that. But if you place a person there or two persons there, and then you can easily see them. If you put a metallic object, large metallic object, you will see that easily. Even the wall can be visible in the bit domain, bit frequency domain. Here we'll use for 1 meter squared aluminum, and we use C-band horn antennas, and cable and coax types are provided in here. On the right-hand side, again, you see the hardware of the front end of the radar. We do not show here the digital signal processing block. We just use the IF signal. Okay. We provide IF signal and then show the bit frequency on the spectrum, or we use a digitizer to convert it and then show the spectrum in spectral domain, show the bit frequency in spectral domain. We can easily implement a peak search and then determine the bit frequency and determine the range and speed appropriately, okay? So here is the system that you'll be building in the next 2 or 3 weeks. So here we see some problems. I will have some others actually. Just now you can start with these problems. I'll stop here. Do you have any question?